All right, going on to topic 7.1, we're dealing with radical expressions, functions, and models. Some of our key words are cube, principal, index, radicand, irrational, and square. Those were in the matching, and I'm assuming you can pick up on that, and we'll mention those as we come to certain things here. So in number 7, they're saying find all the square roots of this particular number. Well, so if we put the square root sign over it, we notice that we can get a positive 8 out of there, and we can also get a negative 8 out of there. Now the positive 8 is referred to as the principal square root, and this is just the other one. So again, square root of this, put the radical sign over it, and this will be a positive 70 and a negative 70. That was just for these. Now, for something like number 9, where the negative sign is outside the radical sign, that indicates our answer is going to be negative. And then we take the square root of 125, which is 15, and the square root of 169, which is 13. So our answer is a negative 15/13. For number 10, they're asking us here to take the principal square root. So we're only looking for the positive square root. So the square root of 256 is 16. Now keep in mind the radical sign is sort of an operational sign, as a plus is an indication of addition, a negative is an indication of subtraction, and so on. The radical sign is square root, or in most cases, again, we'll get to that in some detail. Now, when you get to those with decimals underneath, students have a little problem with that. So this will be 0.9. Oh, let me go try that one again here. 0.3. I got the decimal right. So it'd be the square root of 9, which is 3, and then 0.3 times 0.3 give you your 2 decimal places. For number 12, now here we know the answer will be negative, and it's going to be 0.11, because the square root of 121 is 11, and we need 4 decimal places. So this times itself gives you that. Now in number 13, they're asking us to define what is the radicand. Now by definition, the radicand is what is underneath the radical sign. So I'll just put a red box around the radicand. And they're also asking what is the index, or as I refer to it as the index number. Well, the index number is the number that's in this little notch on the radical sign. And when there is no number there, the index number is 2. So for number 14, the radicand of this is what I have in the red box, and the index number is what is in that little notch, which is 3. Okay, what we had done so far all pretty easy stuff and standard. But now as we get into example 15, we're moving into functions. And again, what I want to present here is a strategy for doing it. So when we had back in earlier chapters, y equals mx plus b, and we were doing little t-charts where we had a value for x, like a value for x would be 2, and this would be 3, and this would be 0, or whatever. Then we just took these values of x and put them into our formula. Well, here they're telling us what our formula is, and they're giving us a value for x. It's 5, 4, 0, and -5. So a strategy for doing this, where you can keep your work organized, is to set up sort of a t-chart. So let's check it out. So here we're going to put a 5 where the x is in the formula. So 3 times 5 is 15. 15 minus 12 is 3. So the square root of 3. Now we're going to put a 4 in there. 3 times 4 is 12. 12 minus 12 is 0. And then the square root of 0 is 0. And then we have a 0 in there. Well, 3 times 0 is 0. So we have under the radical the square root of -12. And here's where a very critical thing happens. That for the square root, is there such an animal or a number that is the square root of -12? And the answer is no. There's no two numbers that you can multiply together, the exact same numbers, and get a negative when your index number is 2. So we say this is not a real number. And in our booklet they're saying this does not exist. All right, when we put a -5 under there, again, this is going to be a -15, and a -12 is a square root of a -27, and that doesn't exist either, so not a real number. Keep in mind that when you multiply two negatives, you get a plus. When you multiply two pluses, you get a plus. So there's no way to multiply two numbers that are exactly the same and get a negative. That's why we say these numbers are not real numbers. Okay, for number 16, again, this is a function expression here. And as we look at the data, they're not giving us t-values, they're giving us p-values. So actually what they're saying is that this function equals 5. So this is what I've set up. This function equals 3, and so forth. And we're asked to solve for z. Well, the way we do this is to get rid of a square root of something. We just square this side, and then we square that. So we square this side, square that. Square this side, square that. Square this side, square that. And then what happens? Our radical sign goes away. So when you square something, it just becomes the radicand. So that makes it a lot easier. Now, when you bring the z squared over to the other side, because we want to put that in standard form because it's a quadratic, this becomes z squared. This becomes on this side, a -10. And this becomes a 25. So that becomes 15. And then when we transpose that, that becomes a -15. And then we say, wow, we have z squared equals a -15. And then you take the square root of that and you have a negative under the radical sign. So when that is 5, it does not exist. Okay, this one is done in a similar way. This is going to become a 9. This just stays a 0. And this becomes a +4. So let's solve these. And I didn't quite give myself enough room here. So I have to work them up. So this is going to be, on this side, when we transpose that, that becomes z squared. This becomes a -10 on this side. And this becomes a -1. Ah, that's going to work. So if we factor this, this becomes the one that's good. Bringing that over to the other side, this becomes a 1. So just bring that over, take the square root of a +1 is 1. And for this one, again, our z squared goes over. And I think I did that one already, didn't I? Okay, this is going to be a 0, so this becomes z squared -10. This becomes, when we bring that back over to this side, a +10. Or actually, we could have left it that way. We'll just transpose the z squared over. That becomes positive. This is 10. And we take the square root of both sides. So this one is the square root of 10. And we bring this over. And that's z squared. And this is 6. The square root of both sides is the square root of 6. Now again, I'm not sure in the class whether they're teaching you this technique, but this is basically what they're looking for. And if I were to do it again, I probably could do it a little better. Okay, we're going to wrap this up here in just a few moments, but looking at this, we're asked to take the square root of this, and keeping in mind that some of these could have been a negative in which we had squared that became a positive. So to indicate that, we use absolute value signs. Now, we know that this is 100, the square root of 100 is 10, but we don't know what was put together to get this, whether it was 2 negatives or 2 positives. So we use the absolute value sign to indicate that. Now for number 18, we see this is a perfect square trinomial that will factor into y minus 5, the quantity squared. And we don't know if somewhere in there was a negative that was squared, so we use the absolute signs for that. Now, for this one, when we see a 3 there as an index number, any odd index number can legally have a negative under the radical sign. So this is going to be a negative 2/3. Because if we cubed a negative 2/3, we would get this. And finally, we've used the word cube too. Now, an interesting thing goes on. If the index number is the same as the exponent, that index number, in a sense, you'll see in a later chapter, is like so. We take away the radical sign, and 6/6 becomes 1, and that will then become x, 5 absolute value of x. So again, I'm jumping ahead a little bit to our next lesson where we use fractional exponents, and we'll give you more detail on that coming up. Again, we can use it. There's a 2 there. So if we take away the radical sign, and divide that by 2, we see we get p to the 25th. And we're no longer, by the way, doing absolute values. And then in number 22, as we said earlier, the square root of a negative number is not a real number or does not exist. And then the square root of 81 is 9. The square root of c squared is just c. And then this is a perfect square trinomial. That would have been 2x minus 7, the quantity squared. So when we take the square root of that, it just becomes 2x minus 7. Okay, that'll wrap us up for today, and we'll pick up shortly. All right, so as we go on, we take a look at example 25. Now notice the negative sign is in the front, so this will indicate that our answer will definitely be negative. And then we're going to take the cube root of 125, which is 5. So then the fourth root of 10,000 is 10. The cube root of a negative 8t cubed, by the way, forgot to put that in there. So the cube root of a negative 8 is a negative 2, and the cube root of t to the third is t. And then looking at that little technique, keep in mind there was a 2 here, and then later we're going to take that index number, divide our exponent by that, and then take away the radical sign. When we do that, that becomes x to the 15th. Now up here they're asking us to do function again, where the function of g is such that the cube root of 2x minus 1. And they're giving us some values for x that we will then put into our radicand. And I've done a little bit of that for you to show you what's going on. So if x is 0, 2 times 0 is 0, and the cube root then of negative 1 is negative 1. And here we put a 14 where the x is. 2 times 14 is 28. 28 minus 1 is 27. The cube root of 27 is 3. Here we have 2 times a negative 13, which makes it a negative 26, and a negative 1, a negative 27. The cube root of a negative 27 is negative 3. And here we have 2 times a negative 64, which is a negative 124, and a negative 1 makes this the cube root of a negative 125, which is a negative 5. Going on to another function problem. Here we have f of t is such that the fourth root of t minus 10. So I made it into a little chart to help organize the data, and we're going to put our value in there. So now we just calculate. So this is going to be 9 minus 10 gives me the fourth root of negative 1. Now again, anytime the index number is even, 2, which we don't write, 4, 6, and we have a negative sign under the radical, then it is not a real number, or the number does not exist. And then here we have the fourth root of 1, and 1's a tremendous number because 1 is a perfect fourth, a perfect third, a perfect fifth. And then here we have a negative 16. And again, it's an even index number, so you can't have a negative under the radical sign. So it's not a real number. And here we have the fourth root of 16, and 16 happens to be a perfect fourth. So that will be 2. Okay. Okay, here we're changing what we're looking for a little bit. Here we want to find the domain of our x. Now, in order to be a real number, it has to be something that does not put, since this has an index number of 2, a number that's negative under the radical sign. So the lowest number we can use here is what will make this radicand a 0. So we're going to use that technique. So it's going to be x minus 4 equals 0, or x equals 4. So if you have a number that's less than 4 under this radical sign, then that number, like for instance, if x were 3 or 2 or 1, it would make this a 0. And of course, if it were negative numbers. So the interval notation for this would be that x is such, well, let's use set builder notation first. x is such that x is greater or equal to 4. Now for interval notation. Well, you're going to have a bracket at 4 and up to positive infinity. So again, if the number were less than 4, like 3, this would be a -1. You can't have that. Okay, again, this is an even number. So take the radicand, equal it to 0, and we have here t is equal to -3. So again, if the number is -3 or greater, that will be okay. But if it were a -4 or -5, that would make this radicand a negative, therefore it's not a real number. So for number 32, set builder notation would be t is such that t is greater or equal to -3. And again, it would be bracket, -3, comma, infinity. Now for number 33, the key to it is, what's the index number? Well, the index number here is 5. That's odd. So can you have a negative under the radical sign? And the answer is yes, because it's odd number. So here we'll say z is such that z is a real number. And interval notation, -infinity to positive infinity. Now, number 34 is a little different, because now our x, in a sense, is negative. So let's solve it the same way. It's even number, index number, so we're going to equate it to 0. And I'll just move this term over, and it'll be 2x and then we're going to get here x equals 2. But notice this is a positive 2. If this were a positive 3, that is bigger than 2, it would make this a -6 plus 4, a -2 under the radical. So in this case, it's a little bit different. So watch what's going to happen here. In interval notation, or set builder notation first, x is such that x is not going to be greater, but it's going to be less than or equal to 2. And when you put it in interval notation, it's coming from -infinity up to 2. So a little twist here, and the reason for the twist is because the x is negative. So remember, negative times a negative makes it positive. So all these negative numbers are good. They're good up to 2, a positive 2, because then this will become a 0. But once it gets higher than a positive 2, it'll make this negative under the radical sign. And with an even index number, you can't have that. Okay, as we go into our last topic that I'll be doing on this section, 7.1, I noticed that I had put a T there, and I now have it radical expressions, yes. So if you've watched some of the others, in a sense that's a bonus point for seeing an error. But here we're doing domain and range. So we're trying to figure out where something is along the x-axis, that would be the domain, and then where it is along the y-axis, that would be the range. And they're asking us to use a graphing calculator to figure out the range. So we have here at number 35 that the function of g is such that it's this. So again, to find the domain, we just equal what is under the radical sign to 0, and we get x is equal to 7. But keep in mind that since x is negative, any positive value larger than 7 will make this negative under the radical sign. So what we have to have here is values for x that are not greater than 7, but less or equal to 7. So there is set builder notation, and that's the proper way to write it. And in our domain interval notation will be like this. Now if I take this expression and put it into my graphing calculator, I end up with a graph that looks like what I have here. So where does the y value start here? Well, it starts here at 0 and goes on to infinity. So our range is from 0, and 0 is included, and it goes to positive infinity. For number 36, we have the function of x is such that it's this. And as we look under the radical sign, again, the index number's 2. So is x negative? Would any value that's of x make this a negative? And the answer is no, because we're squaring all of the negatives, and that will make them positive. So for values of x, x is any real number, because any negative number would become positive. Now, for something like this, you'd have to put that into your calculator to figure out what will the range be. Well, I have it in there, and I don't know if you can see it. Hold it up there a little bit. But I have a sketch here, and the sketch indicates that it's coming from negative infinity, your y values, and goes up to a positive 5. So that's where we get the interval notation for our range. It comes up from negative infinity and goes up and includes 5 in it. Okay, well, we tried to give you some little tips on 7.1. Our next topic will be 7.2, dealing with radical exponents that are in fractional form. And we'll show you the connection between those fractional exponents and radical expressions. They're actually tied in. And a little later on in topic chapter 9, we'll be doing with logarithms. And they deal with exponents as well. So something to look forward to.